Some people are still filing in, but in the interest of time, I'd like to call the meeting to order and welcome you to this special session of the IEEE Power Engineering Society Winter Meeting on the occasion of the IEEE Centennial. Before I get started with the program, let me present a little commercial for the Centennial and remind you that the IEEE Centennial book is just off the press and is available at the table just outside the door of the ballroom. Now, this book is an informal, highly illustrated history of electric power, electronics, and the EE profession, and it is written by John D. Ryder and Donald G. Fink. So it's out there if you'd like a copy. Now, just to remind you of what we're going to do, first of all, we're going to have a slide presentation that will be an illustrated history of the electrical engineering profession, after which we're going to have a panel discussion of the future of the industry. So let me not delay any further and introduce to you Dr. Reese V. Jenkins, who is professor of the history of science and technology at Rutgers University and director and editor of the Edison Papers Project, which is collecting the history of Thomas Edison's activities. Dr. Jenkins has a PhD in the history of science from the University of Wisconsin at Madison, and before going to Rutgers about 5 years ago, he was at Case Western Reserve University. So without further ado, let me introduce Dr. Reese Jenkins.
Thank you. The year is 1884. And the setting is New York. As the nation's largest city, New York boasts a population of 1.3 million people, or nearly 3% of the total population of the country. It is the nation's financial and commercial center and is also the hub of technological and engineering development. Already 3 national engineering societies are headquartered here: the American Society of Civil Engineers, the American Institute of Mining Engineers, and the American Society of Mechanical Engineers. On Broadway is the Western Union Telegraph Company, the nerve center of the nation's instantaneous electrical communication. For a decade and a half, telegraphic stock tickers have provided America's financial community with the latest quotations. In the early 1880s, Alexander Graham Bell's telephones had begun to appear in offices. In September 1882, Thomas Edison had started the continuous operations of his Pearl Street Central Station, providing incandescent lighting service to a small district in Lower Manhattan. A year later, in the spring of 1883, the city had exulted at the opening of the Great East River Bridge between New York and the nation's third largest city, Brooklyn. Edward Weston's electric arc lighting system illuminated this New York monument. Nationally, the year 1884 is witnessing a brief economic recession, and presidential election fever is infecting politics. To the electrical world in America, the International Electrical Exhibition, to be held in Philadelphia in September, is eagerly awaited. Early in the year, a small group of electrical men are worried that there's no national organization concerned primarily with electrical matters to receive foreign guests at the Philadelphia exhibition. A number of foreign visitors, especially from England, are anticipated because the annual meeting of the British Association for the Advancement of Science is being held in Montreal late in the summer. In mid-April, 25 leading figures in the electrical industry endorse and circulate a call for organization of the American Institute of Electrical Engineers, self-consciously modeling it on the American Civil, Mechanical, and Mining Engineers Societies. We reach the climactic day, Tuesday, May 13th, 1884, Early in the morning, the American inventor Cyrus McCormick dies. In New York, the headlines of the papers trumpet the news that Navajo Indians massacred a family, 20 cowboys and 15 soldiers, at a ranch in Utah. The contrast of the city and the receding frontier are apparent. By early evening, a warm drizzle is falling on the cobblestone streets. As the 8 o'clock hour nears, men begin to arrive at 127 East 23rd Street, the meeting rooms of the American Society of Civil Engineers. A large and enthusiastic group, largely from New York, gather, and meeting begins with the discussion and establishment of the rules of organization and membership. A little later, ballots are cast for officers, and Norman Green, president of the Western Union Telegraph Company, is elected the first president of the new American Institute of Electrical Engineering. Many of the other officers are drawn from the telegraph community. However, those in attendance include many involved in electric lighting and a few from the telephone industry. Prominent names among the vice presidents and managers are Thomas Edison, Alexander Graham Bell, Charles Brush, Stephen Field, Elisha Gray, Edwin Houston, Theodore Vail, and Edward Weston. As the enthusiastic meeting draws to a close, Nathaniel S. Keith, secretary of the AIEE, reads a letter from the U.S. Patent Office examiner for the class of electricity. After several resolutions are passed, the first meeting of the AIEE is adjourned. The goal that was the initial impetus for establishing the AIEE is addressed during the ensuing months. The organization is given free use of rooms in the exhibition building during the International Electrical Exhibition in Philadelphia from September 2nd to October 11th. Many domestic members and foreign electricians visit the new association's rooms. On October 7th and 8th, the first formal professional meeting is held at the exhibition with the presentation of 12 technical papers. Hence, between March and October 1884, a national professional organization of electrical engineers was established. Significantly, the initial leadership in the organization came from the telegraph industry, the principal area of application of electricity until the advent of telephony and commercial electrical lighting in late 1870s and early 1880s. The professional meeting held in early October 1884 carried the symbols of the then past, present, and future of electrical engineering. The leadership of the organization, predominantly from telegraphy, represented the past. The emergence of strong influence of electric lighting and power seen in its dominance of the papers presented at the meeting reflected the then present and near future. Yet, the AIEE's first professional paper, Edwin Houston's On the Edison Effect, foreshadowed the importance of electronics to electrical engineering in the future. The founding of the AIEE also in part reflected the values and the attitudes of American society at the time. In its first century, the nation had held a subordinate position to Europe in leadership in science and technology. The 1876 Centennial Exhibition in Philadelphia symbolized America's technological coming of age, yet in areas closely related to science, especially chemistry and electricity, Europe was still considered preeminent. The Society of Telegraph Engineers and Electricians, which later became the IEE, had started in England in the early 1870s. With the potential of foreign electrical engineers arriving, American national pride proved the stimulus for creating a national organization, largely with the leadership of the local New York Electrical Society. Another aspect of American culture provided the setting for American electrical engineering, even before the founding of the AIEE, and has continued as a strong element over the past century. From the founding of the American nation, the conflict between centralized and local control has been strong, whether reflected in the tension between state and federal rights or between the individual and the state. Likewise, the conflict between central and local control, between government and individual control or ownership, has marked electrical engineering design. Like the balance of powers in the Constitution, a balance of social values and technical traditions have marked major engineering achievements. Two early examples are striking. In telegraphy, by the 1870s, the American system was a national network with centralized coordination, regional input of electrical energy into the line, and local control of message sending and receiving. Likewise, Edison's Pearl Street Station, the model for generation and distribution of electricity for incandescent lighting, was designed with a central generating station, but with local control of the lighting. Edison's system was modeled on urban gas lighting. Gas had to provide highly reliable, continuous service because if the gas pressure fell, the flame would go out, and then when the pressure was restored, the occupants would be asphyxiated. Urban gas systems employed central generators and stored gas under pressure in order to provide this necessary continuous service. In order to compete with gas, Edison's system required continuous service also, but electricity could not be stored in tanks, as with gas. Therefore, Edison and power engineers since have worked to provide continuous and responsive service to customers. The individual consumer controlled the lamp, and the central station had to be responsive to the consumer demand. That important value, established during the incubation period of electric lighting, has set the pattern of consumer expectations and engineering design for a century. As we look at a century of electrical engineering with special attention to power engineering, we see three approximately equal periods. First, from the 1880s through the teens. Second, the 1920s into the 1950s. And third, from the late 1950s to the present. Each period reflects important new horizons and directions in electrical engineering, and each reflects patterns of centralization and decentralization. Rapid electrification, the emergence of AC, and early development of radio dominated the period from the 1880s through the teens. By late in the 1880s, more than 180 Edison central stations were installed across the United States. Clearly, the incandescent light and central station had triumphed over the arc light and isolated station. But in the 1880s, also, the direct current system encountered the serious challenger, AC. Edison and his associates sought to thwart the adoption of AC, charging that AC was far more dangerous to life than DC. During the 1880s, Edison continued to dominate not only the construction of power generating plants across the nation, but also the electrical companies manufacturing the generation and distribution equipment as well, companies that soon became the General Electric Company. However, entrepreneur and inventor George Westinghouse drew upon the theoretical and practical work of several electrical engineers to introduce a competitive AC system. Perhaps influenced by his personal experience with high-pressure transmission of gas, Westinghouse in the mid-1880s drew upon European ideas regarding AC and set William Stanley to work in a laboratory at Great Barrington, Massachusetts. The Westinghouse AC system, employing transformers in a parallel circuit, was commercially introduced in 1886, and soon Westinghouse sold a large number of AC central stations. The great advantage of AC system envisioned by Westinghouse was the efficiency of transmitting electricity at high voltage and using transformers for provision of electric power at low voltages to the consumer. Where DC stations were only practicable in high-density urban areas, the AC system made practicable electrical supply to suburban, low-density population areas as well. The introduction of the AC system allowed for larger-scale generation and consequently more centralized production of electricity than possible with the DC systems as designed in the late 19th century. Two major engineering developments were critical to the rapid acceptance of the AC system in the United States. The first was the design of an effective AC motor so that the usefulness of AC electrical power could be extended to industry. European work on AC motors in the middle 1880s climaxed with the achievement of Nikola Tesla, who presented in May 1888 at a meeting of the AIEE a significant paper on AC motor design. Tesla's patents on the polyphase induction motor soon came under control of Westinghouse, who continued development work in order to make it commercially practicable during the middle 1890s. The second major development was the introduction of the high-speed steam turbine to replace the slower and less efficient steam engines which were used to drive the direct-connected AC generators. Drawing upon European turbine designs developed in the 1880s, Westinghouse introduced turbogenerators late in the century, and GE soon followed. These machines provided substantial savings in operating costs. Also, because they were much smaller, weighing only 1/5 as much as equivalently rated reciprocating steam engines, they provided lower initial costs for the prime mover. In 1893, the Niagara Falls Power Company chose AC as its method of generation and transmission. Its successful operation beginning in 1895 symbolized the triumph of AC over DC for large-scale central station generation and transmission. DC did not disappear as the work of Frank Sprague from the 1880s and of Thomson Houston Company, which combined with the Edison's companies eventually became GE, placed DC at the heart of electric traction. Between 1890 and 1910, electric traction grew rapidly for both municipal transit and for interurban transportation. It played an important role in the development of what became known as the streetcar suburbs, the initial phase of an urban decentralization which electricity, automobiles, and trucks have fostered to the present time. During the first 2 decades of the 20th century, central stations became increasingly important. Industrial use of electricity increased markedly, but with improved transmission, the central station, instead of the isolated generating plant, increasingly provided the electrical service. High-voltage transmission, especially in the West, connected remote hydroelectric facilities with distant metropolitan areas. Increasingly, utility entrepreneurs such as Samuel Insull in Chicago interconnected their central stations in order to facilitate load diversity, to provide improved reliability, and to lower costs. Electrical engineers provided the theory, design, and know-how for the development and installation of increasingly complex and sophisticated generation, transmission, and distribution facilities. By the turn of the century, the leadership in electrical engineering had shifted from the inventors and rough-and-ready operators from the practical school to those graduating from formalized electrical engineering programs in the nation's leading colleges, technical schools, and universities. Likewise, institutionalized research, pioneered by early electrical experimenters such as Thomas Edison at Menlo Park, New Jersey, became the pattern among the major electrical manufacturers such as General Electric, Westinghouse, and Bell. Theoretically oriented designers such as Steinmetz played key roles in translating rapidly changing theoretical and mathematical concepts into practical applications. Between the turn of the century and 1920, electrical generation increased nearly 10-fold, and central station output increased nearly 15-fold. During that period, electrical rates were cut in half, as nearly half the urban and suburban dwellings in the United States had electricity. Yet, less than 2% of farm homes had service. During the period from the mid-1890s to the early teens, a new area of electrical engineering emerged: wireless, or radio. With notable leadership from Marconi, and especially with the success of his transatlantic broadcast in 1901, a cadre of young radio experimenters emerged. By the early teens, these young experimenters became increasingly self-conscious of the distinctiveness of their work in the context of the dominant power engineering interest in the AIEE. In 1912, they established their own professional organization, the Institute of Radio Engineers. But we shall hear more of electronics in the IRE later. Clearly then, between 1884 and 1920, electrical engineers, power engineers in particular, had created many new horizons, and had initiated an energy revolution in the urban home and factory. Already, a strong trend of centralized production and control of electrical distribution was underway. A drive toward ever larger output of generators was offset by efforts to reduce the size of turbogenerators per unit of output. Transmission line voltages were being increased, and yet, fundamental to the nation's electrical supply system was the basic premise that the utility had to respond to the consumer's demand for service at any moment of the day or night. Ultimately, the consumer was in control. Electrical engineers had to design the system to respond reliably to that control, and utility executives had to plan and finance the power systems. During our first period, the 1880s to 1920, the basic direction for power engineering was established. As we now turn to our second period, from the 1920s to the 1950s, the new horizons in power engineering lay in integration of power systems, increased scale of generation and transmission, and in development of new applications for electricity for the home and factory. By 1920, many utility companies had interconnections among their own power stations. With increased concern for protection of high voltage lines and transmission systems from lightning, major improvements in transmission line protection were developed in the 1920s and 1930s. As transmission voltages increased and interconnections among utilities developed, financial integration of companies also increased. Between 1920 and 1948, the number of private utility companies decreased by 4/5, while generation increased nearly 7-fold. One of the pioneers in interconnection among companies was the Pennsylvania-New Jersey interconnection. Based on an agreement signed in 1927 among Public Service Electric and Gas, Pennsylvania Power and Light, and Philadelphia Electric, the Pennsylvania-New Jersey interconnection employed both 220 kV and 66 kV lines to take advantage of load diversity among the three companies and to treat the combined generating units as one system, loading the generating units for maximum economy. The success of this interconnection led to its expansion in 1956 to the Pennsylvania-New Jersey-Maryland interconnection with the inclusion of Baltimore Gas and Electric. In the mid-1930s, two 287 kV lines connected the Hoover Dam on the Colorado River with Los Angeles, and a third line was completed in 1940. Likewise, in the 1930s, TVA and REA brought whole new dimensions to power engineering and to public power. Clearly, high-voltage AC transmission had introduced ownership and generation control at the regional level. As improved telemetering and communications developed, increasingly centralized control was possible for ever larger regions. Another pioneer in the development of high-voltage transmission and regional interconnection was American Gas and Electric. Led by Philip Sporn, an electrical engineer and executive with unusual vision and drive, American Gas and Electric invested in research and development of high-voltage transmission, protection, and control. During the 1940s, the company developed a basic design for a new level of transmission, a 345 kV system. The first link in this system went into operation in 1953 and eventually became part of a system extending from near Chicago to Roanoke, Virginia. Meanwhile, electrical and mechanical engineering developments in the design of turbogenerators led to new levels of production efficiency. Between 1925 and 1950, metallurgical improvements, changes from cast iron to cast steel to alloy steels, encouraged a 50% increase in steam temperatures and a nearly 500% increase in steam pressure. As a consequence, turbogenerator ratings quadrupled and fuel consumption per kilowatt hour nearly halved. At the same time, rates charged customers were less than half. Associated with the new opportunities that power engineering was creating were important questions of public policy. The share of the population that enjoyed electrical service grew dramatically between 1920 and 1950. Service was extended from a little over 1/3 to 95% of all U.S. residences, with the most dramatic change coming in the 1920s. Yet, in 1920, less than 2% of farm dwellings had service, and by 1930, still only 10% had such service. By 1950, nearly 80% had electricity. Clearly, by the end of the 1950s, the combination of regional expansion of companies, improvements in transmission efficiency, the lowering of electrical rates, and the action in the public sector, especially the achievements of REA and TVA, aided in bringing electrical service to the entire nation, and electrical output increased 15-fold. The work of mathematically oriented engineers like Edith Clark and increasingly intimate links to physics fostered new levels of achievement. Widespread availability of reliable electrical service and strong advertising programs from utilities and manufacturers encouraged broad adoption of domestic appliances that transformed the American home. In the post-World War I era, irons, fans, toasters, vacuum cleaners, and washing machines became increasingly common. In the late 1920s and 1930s, refrigerators and even electric ranges grew in popularity. Another domestic appliance, the radio, became commonplace and set new patterns of recreation in the 1930s and 40s. KDKA, Pittsburgh, pioneered in 1922 in commercial broadcasting, and soon American homes were filled with radio news, sports broadcasts, music, and dramas. Emerging in the 1930s, centralized radio networks centralized the programming production and set national patterns to be followed with the introduction of television in the late 1940s. The automobile is generally not regarded as an electrical vehicle, but the electric self-starter, electrical ignition system, lighting, and metering systems in the car meant that the automobile could not function without electricity. While ownership and production of electricity was increasingly centralized and the transmission and distribution encouraged both domestic and industrial decentralization, the automobile, the truck, and radio reinforced decentralizing tendency which culminated in suburbanization and the breaking of the social barriers between farm and city living. Electrical engineering also played a key role in the military efforts associated with World War II and the Cold War. Radio and electronics were highly visible in the war effort and in new directions in research. Power engineering played its part in meeting the demands of industry for wartime production and remarkably also meeting domestic demands in the face of broad domestic energy, material, and manpower shortages. During the period from 1920 to the 1950s, the new horizons lay in the integration of power systems, increased scale of generation and transmission, and development of new applications for electricity for the home and the factory. As we turn now to our third and last period, the past quarter century, power engineering has continued to create new horizons in a period of rapidly changing technical, economic, and social change. The introduction of nuclear power, new engineering and organizational approaches to reliability, the rapid assimilation and exploitation of the computer are dominant themes during the past 25 years. In the wake of the shock and devastation of the atomic bomb, power engineers, in cooperation with other engineers and scientists, took the initiative in leading the way to the peaceful uses of atomic energy. The construction of nuclear power plants represented a special engineering challenge, building an entirely new power-generating system. The initial enthusiasm for the nuclear program was excited by forecasts of low production cost, growing scarcity of traditional fuels, continuing rapid increases in demand for electricity, and less environmental pollution. With the passing years, the social and economic environment changed dramatically, and the nuclear program, one of the engineering marvels of the century, is now in serious jeopardy in the United States. At the same time, the social and economic forces which have so seriously affected the nuclear program have also altered some of the traditional patterns of power engineering and the electrical supply industry. The success of power engineering in placing electrical power at the very core of modern life has had substantial social consequences. Because of the centrality of electricity to our lives, and because of the traditions of responsiveness to the consumer and of a very high order of reliability of service, expectations have risen and today are very high. We all remember the late afternoon of November 9, 1965. Just a little over 18 years ago, the Northeast blackout affected the service of 30 million people and stunned the nation, the utility industry, and the power engineering community. It became clear how vital electrical energy was to our modern society, and as a consequence, how high consumer expectations were. It also became clear that with ever larger generating units, rapid growth of systems, and stronger interconnections, there had risen substantial vulnerability to the spread of the transient effects of sudden disturbances. In the wake of the Northeast blackout, there soon were organized regional coordinating councils, and in 1968, the National Electric Reliability Council was established to collect and disseminate reliability criteria and to spur planning, construction, operation, and control procedures for interconnected systems. While consumers expected the historic trends of stable or falling rates to continue, instead, the late 1960s and 1970s witnessed an increasing concern for environmental impact of power plants, whether nuclear or fossil fuel. Sharp increases in fuel costs, especially for oil, sharply increased regulation at all levels of government, and an inflationary economy in the 1970s with high interest rates. Consequently, energy costs skyrocketed. Growth in consumption of electricity slowed markedly, and the direction for engineering creativity shifted, at least in part, from increased production and large-scale production economies to conservation, more efficient utilization of energy, and alternative fuels. Thus, changing values and conditions within the social environment have helped to set some new goals and agendas for engineering. At the same time, some of the traditional directions and values have continued. One of the important continuities is continued improvements in generators and continued integration of systems and even higher transmission voltages. By the late 1960s, 345 kV was adopted by many utilities in the Midwest, in Texas, Oklahoma, New Mexico, and Arizona, and in the Northeast. Soon, 500 kV followed. And in 1967, American Electric Power completed the first line of a 765 kV system to overlay its 345 kV lines. Meanwhile, today, a number of research and testing programs are working on 1100 kV. At the same time, high-voltage long-distance DC transmission was introduced in the early 1970s with the Pacific Intertie linking the Northwest Pacific region with Southern California. The advantages of the long-distance DC transmission, less costly lines, lower transmission losses, and insensitivity to many systems problems that restrict AC, are encouraging the present development. Because of the economic advantages, interconnection, now even across national borders, has been a trend that has continued since the turn of the century. Key to the success of interconnection has been the development of sensitive metering devices, telecommunications, and computerized controls. Electronics, whether in communications or information and data processing, have transformed our lives and also have helped to revolutionize power engineering. In 1912, the IRE was established, separate from the AIEE, but in 1963, the two merged to form the IEEE. The prominent role of electronics, computer engineering, and systems engineering in power engineering has marked the last decade. Perhaps the most significant application is in the control rooms for interconnected systems. The information, the variables, the decisions are very complex. The real-time information and the forecasts are both vital to the decisions that affect system stability, reliability, and ultimately consumer cost. But of course, the computer is also playing a key role in customer service, in engineering design, and in the research laboratory. Yet this design, problem-solving, and customer service are geared to the three constants of the past century of power engineering. The three R's: responsiveness, reliability, and research. When Thomas Edison designed his Pearl Street station, the premise was that the station had to respond to the consumer's demand at any moment. The ultimate control was in the hands of the consumer. Today, in the control rooms of the power pools and interconnected systems, generators are started or shut down, and power is switched from district to district, oftentimes by computer, in response to consumer demand. At the same time, these interconnections help to provide the backup in case of unusual demand or accident, guaranteeing steady, reliable service throughout the nation. But behind the first two R's of responsiveness and reliability is the foundation, the third R, research. Whether in the laboratory facilities of major manufacturers such as General Electric or Westinghouse or small suppliers, whether in joint research efforts through EPRI or efforts of individual companies such as Consolidated Edison or American Electric Power, or whether in a federal installation or university laboratory, research is the foundation for the creative new engineering ideas for the horizons of the future. In the past century, the three R's have reflected historic American values. While electrical engineering has helped to create worldwide transportation and communication capabilities, as well as to play a key role in space exploration and defense, power engineering has built ever larger power systems with increased centralization of control, and yet with an ever wider availability of electricity throughout the land. Along with the automobile, the truck, and electronic communication, dispersed electrical service has encouraged suburbanization of manufacturing and the suburbanization and recently the ruralization of the population. Some predict that in this environment, the microcomputer in the home may return us to a work pattern of the past, the cottage industry, the ultimate in decentralization. American values have also placed a strong premium on size. American engineering achievements typically have emphasized bigness, whether it is the span of a bridge, the height of a skyscraper, or the rating of a large generator. But the true value here seems not to be exclusively on bigness, but upon the degree to which it departs from the human scale, the macro and the micro. Hence, American engineering also takes pride in smallness. Smallness per unit of capacity, whether in the size of a radio, computer, or even a power generator. In either case, we take pride in that apparently ultimate value, the new. Traditional American values reflected in the past century of power engineering achievements include an emphasis upon size, growth, newness, and centralization. But at the core are the three R's of responsiveness, reliability, and research. The challenge for engineers of today is to address imaginatively and with integrity the changing technical demands and social expectations in order to create the new horizons for the second century of electrical engineering. Thank you.
Well, thank you very much, Dr. Reese. If our panelists could come up here and occupy their places on the stage, we'll continue. And while they're moving up here, let me just define the format that we're going to follow. First of all, I will ask each of our panelists to come to the lectern and make some semi-formal remarks. And afterwards, I'm going to try my best to get them into a discussion among themselves. And when that's over, we will entertain questions from the audience. And that ought to make for the continuation of a fine session. Let me move over here. Is this microphone on? All right. Well, first of all, in the program, you will find biographies of each of our three panelists, and I won't read those to you. I will simply make the observation that, to me, first of all, these three gentlemen are engineers, and not just ordinary run-of-the-mill engineers. Each one of them, their engineering accomplishments have been recognized by their election to the National Academy of Engineering. Then, on top of being first-class engineers, each is or has been the chief executive officer of a major corporation, major utility, with one of them even having switched hats here in the recent past. So the combination of these two things really qualify these gentlemen quite well to talk about the future of the electric power industry. So without further ado, let me introduce, first of all, William R. Gould, who is chairman of the board of directors and chief executive officer of the Southern California Edison Company. Mr. Gould. Yes, fine.
Thank you very much, Herb. I can't tell you how much I enjoyed that last presentation. It was just like seeing the history of everything that I had hoped and dreamed of a professional career unfold. And so it's with a little bit of emotion that I approach the podium today. But ladies and gentlemen, there's another aspect of emotion here too. In the last 24 hours and going among the halls and meeting old friends and whatnot, it's been rather a sentimental journey for me to be here. I grew up in the afterglow of the Old West, and there's a story, I guess, that kind of applies to this gathering here today. This story treats the situation of the mining town in which there were several saloons and one church. And on one occasion, tragedy occurred. The church burned down. The pastor went the next morning to the proprietor of the largest saloon in town, and he said, "Since your enterprise has a low load factor on Sunday morning, I wonder if we might work out a interconnection agreement whereby after your festivities on Saturday night, we might use your facility on Sunday morning until we build a new church." The proprietor of the saloon thought that was a fair and equitable proposition, and he said, "Yes." He says, "It may be that you'll have to clean up the place a little bit after Saturday evening, but you're welcome to do it." So came the first Saturday evening and Sunday morning, and that procedure was followed. The faithful parishioners came in and cleaned up the place, and along about 9 o'clock the next morning, there was gentle piano music emerging from the saloon, and the pastor was standing at an improvised podium at the bar, and he was about to begin the service when someone recognized that there was a cage containing a parrot over in the corner of the room. No one had uncovered it, and they walked over and uncovered the parrot cage. The parrot blinked at the light for a moment and looked around, looked over at the bar, and he said, "New bartender." He looked over at the piano and says, "New piano player, too." He looked over at the ladies in the choir, and he says, "A new group of dancing girls." Looked out at the congregation and says, "Same old crowd." Well, I think that we have perhaps some of the same old crowd here, growing a little bit older, but it's a great crowd, and I'm humbly proud to be part of it. I would like to say just a word to structure the remarks that I'm going to make. I'm going to talk to you about our approach, the Southern California Edison approach to the future. It's going to be a little unique. Some of you may surmise some of the areas in which it will. But as I speak, let me be sure that you recognize that Our company has almost a 100-year history. It will have in 1986. Our beginnings were with a predecessor company in 1886. Also, I think we have something of a proud, or at least an acceptable, engineering tradition and heritage. We grew up as a hydro company. We pioneered a number of the lower voltages, and finally we pioneered the 220 kV voltage in the 20s. We did a few other things that were unique, such as area load frequency control to give an acceptable frequency control for the movie industry. We also took our place in the thermal escalation of temperature and pressures. Did a few unique things there, including a computer-controlled plant that on the first time the turbine rolled, we rolled it and started the plant with computer. It was the sixth plant that we'd attempted to do this. We did it successfully and then concluded it wasn't worth it. We also, very briefly, had the world's largest nuclear station in operation, and also for a few months or several years, it turned in the finest performance of any nuclear station. And coming to the recent months, I guess I hold the distinction of being the executive of the most recent utility to put 2 new nuclear units in service in an atmosphere that is has the more familiar situation of nuclear plants being abandoned or not going into service. So if you would remember this as I tell you our approach to the future and recognize that we do have our heads screwed on right, I think that this might be helpful. So let me embark on my formal remarks. Our nation's electricity fraction, the percent of energy that is used for electrical production compared to total energy consumed nationwide, is projected to reach 45% by the year 2000, and to approach 55% by 2020. The fraction grew from approximately 17% in 1950 to over 33% in 1980. The trend is clear. The importance of electricity to our nation's economy and quality of life will increase. In other words, whatever else we may debate about the future, there will be an electrical future and a future for electric utilities. Also, while displacing fuel oil is not as economically important today because oil prices are currently stable, our country and our industry eventually must reduce dependence on oil and natural gas. The Middle East continues to be so volatile that any of several events could serve to disrupt the flow of oil to the free world. Despite our somewhat reduced level of imports as compared to 1973, this could bring with it an attendant economic and national security problem such as we experienced during the recent OPEC embargo. We in the electric utility industry are employees of a highly regulated enterprise. We serve the people through representatives that they elect and that they subsequently appoint to regulate us. The future of our industry depends to a major extent on customer acceptance. We serve at the sufferance of our customers. More than ever before, corporate decisions must be measured against this test. What is the impact upon the customer? At Southern California Edison Company, we plan for the energy future of more than 9 million people in an environment of fluctuating interest rates, rising construction costs, an uncertain regulatory environment, changing prices, and reliability of supply for the fuel for our generating plants, and less certain projection of capacity and energy requirements. In order to minimize the impact of these variables, we have all our present and future resources while ensuring reliability, affordable electric power for our customers. Both national and regional trends profoundly affect strategic planning. For example, regional influences played a major role in Southern California Edison's decision to accelerate development of renewable and alternate energy resources. Utilities in other regions affected by different factors have become pioneers in other ways. For example, in diversification and fuel conversion efforts. California is regarded by many as a bellwether state for good and evil. It is possible that current conditions in which California utilities conduct their business might someday impact other areas of the country. Today, I want to present my company's experience as a case history and a look at one utility's response to the emerging business environment facing our industry. Southern California Edison particularly benefits from several factors, including proximity to several generating resources. Another advantage is that resources in our service territory, such as hydro, solar, wind, and geothermal, are frequently available when most needed. They tend to match the system's afternoon summer peaking characteristic. The state has a broad industrial base characterized by innovative technology, particularly in the aerospace and electronics sectors. This generally provides for a receptive attitude on the part of the public, business, and political sectors regarding development and deployment of renewable alternate technologies. Finally, the majority of the country's renewable energy hardware manufacturers are located in California, where government at all levels has encouraged development of renewables and alternatives. Such institutional support, moreover, tends to underscore the importance of developing renewable resources and emerging technologies to continue to meet the expanding needs of new industry and a growing population while reliably serving existing customers, protecting the environment, and providing our shareholders with a fair return on their investment. Our continuing challenge is to meet successfully the needs of all of our constituencies. The success of our renewable and alternate programs will depend on the public perception of financial, environmental, health, and safety considerations. Nuclear power safety and coal plant stack emissions are likely to continue as issues in the 80s and 90s. As long as technology is publicly perceived as inherently dangerous, its development and use carries implications that are more potential than technical. Delay of plant construction and power production from coal and nuclear generation are likely so long as this perception exists. However, there are solutions to such problems. The public disquiet can be depoliticized by forthrightly addressing public concerns and communicating very openly and honestly with the customer. It is incumbent on all sectors of the electric utility industry as a steward for its customers to develop a sensitivity to their concerns and perceptions. Technical responses will be required, for instance, should we encourage simplified and standardized nuclear and coal plant designs. At the national level, safe, long-term nuclear fuel reprocessing and high-level waste disposal should be ensured through prompt implementation of Nuclear Waste Policy Act of 1982. We should also focus increased attention on the human engineering aspects of critical power plant operations, and we must develop better understanding of the interactions involved, such as radiation effects on materials. As a technological response to public concerns, renewable and alternate resources offer additional sources of electricity. Modular systems additions and the lack of some negative characteristics that cause public opposition. However, developing significant capacity in the form of modular-sized plants can be undertaken only through a major commitment of corporate resources and direction that leads to plants of higher quality and shorter construction lead times. Electric utilities must also lengthen planning periods. It is a time now to consider system requirements and even new technology solutions beyond the year 2000. I can't emphasize too much that during quiescent periods, we should not reduce our research and development activities. We should prepare while we have the time. While capacity that generates renewable resources can be built faster, the technology must have attained commercial operation. Development and demonstration of new technologies require extensive capital, labor, material, testing, and time. Investment in technologies such as fusion, solar satellites, and refined and expanded solar power must be made now if their contributions are to be available when they are needed. For instance, improvements in the technologies of coal gasification, advanced coal combustors, and fluidized bed coal combustion must all be expeditiously and vigorously pursued today to be available as an option for the late 1990s and beyond. Although coal is not a renewable resource, it is a plentiful domestic resource, and it can be used effectively for electric generation. But it must be made environmentally acceptable. Last year, an integrated coal gasification combined project at our Coolwater Station completed capital financing from participants and won operation support from the U.S. Synthetic Fuels Corporation. The plant is scheduled for completion in mid-1984 and will convert coal into clean-burning gas to power a 100-megawatt generating facility. This will be a combined cycle facility. Further encouragement for synthetic fuels development came in December when the Synfuels Corporation invited the Great Plains Coal Gasification Project at Beulah, North Dakota, to apply for up to $2 billion in loan guarantees and price supports to $2.7 billion, $67 per barrel, for the Union Oil Shale Project in Colorado. Although this federal assistance to alternate resources is currently editorially unpopular, these emerging technologies must have this support in their development stages as other technologies received various forms of assistance in the past. To develop technologies that are alternative to conventional electric generation processes means the creation of entirely new industries. Ecological effects, the optimum mix of small, medium, and large industrial plants, and integration of the new technology into actual operation with the existing system must be better understood. Southern California Edison's adoption of a commitment to a renewable and alternate resource program is an example of a new utility corporate policy designed to meet the changing business environment. Until the early 1970s, energy prices were relatively stable, and the real price of electricity had fallen because of abundant and inexpensive fuels, technical developments in generation and distribution, and economies of scale in ever larger and more efficient power plants. Demand for electricity increased steadily at 7% per year or greater, and most of us thought that it would go on forever. We discovered after the 1973 oil embargo that our operating climate had changed dramatically. Previously inexpensive and abundant fuels became costly, scarce, and potentially unavailable. Inflation and double-digit interest rates were making project financing a nightmare. Large, economical, centralized generating stations were increasingly difficult to build. Economies of scale no longer applied, and there was increased government regulation and public intervention. We gradually realized that existing conventional technologies, oil, gas, coal, nuclear, were by themselves currently inadequate to meet future electricity requirements. There came a glimmer of a question that we faced as a corporate body. Was it time to set the old procedure aside, if only for a few years, and do something different? Customers were seeing their electric bills go up dramatically, and at the same time, the electric industry was experiencing severe financial problems. Based on our company's foundation of nuclear, coal, hydro, baseload production, and the achievement of some significant successes in research and development, we felt we could consider accelerating the development of alternate and renewable resources, and in so doing might better serve the interests of our customers and shareholders as well as the total public interest. The adoption of a strategy for accelerating the development of alternate and renewable resources would do these things for us: reduce the near-term need for large capital-intensive generating plants, decrease the dependence on costly and potentially unavailable fuel oil and natural gas. We had up to that point been the utility that burned the largest amount of oil of any utility that I know of, here or abroad. Provide generating flexibility and meeting changing load forecasts. In other words, with small components, we could apply a vernier to the forecast of load